but the lights that are off is not working, so I'm sorry about the dim lighting today. There was a typo apparently in my presentation last time of the convolution. There was a part where I was, so let's do a correction. Some folks came up to me last time and pointed this out. We had an impulse response that was just two spikes. Like so. At 5 and minus 5. And there was an x of L that was like this. And we said that when we want to construct x of n minus L, you'd flip. When you flip, the front end will be the short lollipop. Okay? And n takes the location of the short lollipop to n. So this would be n, this would be n minus 1, and this would be n minus 2. Okay? And when we wanted to figure out what the output is corresponding to the filter that has this as its impulse response, that as its input, where did we say the first non-zero overlap occurs between x of n minus L and h of L? So if we're doing the product x of n minus L times h of L, where is the first n for which there is non-zero overlap? Negative 5. N equals minus 5 is the smallest value of n for which h of L and x of n minus L have a non-zero overlap. Which means smallest n for which y of n is non-zero. Okay? And so when we wanted to figure out y of minus 5, we had to look at, to determine, we look at minus 6 and minus 7. This is 1, 2, 3. We look at x of minus 5 minus L. And the typo, I think, was that I put 5 minus L. So look at your notes and fix that part. This is x of minus 5 minus L. You pointwise multiply it by that h of L to get the first non-zero value of the output. Whose notebook was this? Thank you. Did you find it? Ooh. So the moral of the story is when you want to do the flipping and shifting that's involved in convolution, you first flip. And then the front end of the signal goes to n. So if n is positive, you're shifting to the, after you flip, you shift to the right. If n is negative, after you flip, you shift to the left. And if you keep that in mind, you should be okay. Lighting is bothering me for some reason. Okay, so let's resume where we left off, though. So we were talking about frequency response. This is where we start. This is the place in the course where we start getting into real signal processing. So up to this point in time, it was all just a bunch of math. It'll still be a lot of math, but at least now you begin to see the real-world applications. So again, we have our LTI system with impulse response H, input X, output Y. And we know that the output is the convolution of the impulse response and the input. The dummy variable doesn't matter. It can be K, L, whatever. We used a special input signal, looked at the input signal that's the complex exponential. Okay? Single frequency omega, complex exponential input. And one of the things that I've been saying is that LTI systems act on complex exponentials in a very special way. So there's a special relationship between complex exponentials and LTI systems. When we did this, and we plugged it into the convolution equation, well, in the convolution equation, we need x of n minus k. So wherever I see an n, I replace it with n minus k. And I can write this as e to the I omega minus I omega k, e to the I omega n. And I plug it into the convolution. So I have summation over k. I'm not going to keep carrying all this minus infinity to infinity. Summation over k, h of k times x of n minus k. X of n minus k is e to the minus I omega k times e to the I omega n. The summation is over k. This complex exponential has no dependence on k. So I can pull it out of the summation. That's what we did. And when you look at this box here, you have something that's a function of k times something that's a function of omega and k. And the product of these two forms the kernel of this summation. So you're summing over k. What's going to be left? What kind of a function? Omega. We call that with the capital letter H, H of omega. And this is the frequency response of the filter. So, in the time domain, we have h, or h of k values. In the frequency domain, we have h of omega, and its relationship to the time domain impulse response is that it's the summation from minus infinity to infinity, h of k e to the minus I omega k. At this point in the course, we have found the relationship that takes us from the time domain to the frequency domain. Obviously, we would like another relationship that takes us from the frequency domain back to the time domain. So if I give you the frequency response of a filter, you can tell me what the impulse response was. We do this hopping quite frequently in signal processing. But we're not yet equipped to do that. That's a discussion later on when we talk about Fourier transforms. So this is this you'll find is the transform of the impulse response. And we need an inverse transform relationship that takes us back from the frequency domain to the time domain. But don't worry about that for now. So right now we have this function of omega that tells us how the impulse response in the time domain maps to how this filter, how this system treats various frequency components. Notice this is dependent on omega. As you change omega, the value of h of omega will change in general. And that's where the name filter comes from. For some frequencies, omega, in the input signal, h of omega may be 0, which means the filter kills those frequencies. For some frequencies, omega in the input signal, h of omega may be a high value. So it passes those frequencies, or it may even amplify those frequencies. So there is an analogy with the physical sieve that you use to sieve maybe flour in the kitchen. The only difference is in the kitchen, some particles stay on top of the sieve, some pass through, but a mechanical sieve never amplifies anything, right? But in signal processing, the filter, which acts kind of like a sieve, can actually amplify certain frequencies. H of omega may go over the value 1, for example, for some frequencies. And may go down to values near 0 for others. And we'll do some examples of these today. All right, so let's start with an example. Here's an example. A system has impulse response h of n, which is 2 spikes. 1/2 at 0 and 1/2 at 1. And it's 0 everywhere else. Okay? You should have no trouble converting these variables to the dummy variable k or l when you plug this into the convolution expression. So here's what I want you to do with this. Here's your system. That's the impulse response. You have an input signal x, you have an output signal y. The first thing I want you to do is express y in terms of x. Okay? And after you do that, I want you to determine the frequency response. H as a function of omega. Now, for those of you who dabble in the stock market, this would end up corresponding to a 2-day moving average. That's what it ends up being. So that should guide you with respect to the answer to the first question. So this filter, if you apply it to the stock price data, for any given day, today for example, at the end of today, it gives you the average of today's closing price and yesterday's closing price. And that's what I want you to come up with when you write the expression. So use the convolution of the input signal x. I haven't told you what the input signal is. Just use an x. Convolve it with this signal, with this function, and tell me what you get for y of n. That's part A. And you need to talk to your neighbors, because this is quite new to most, if not all of you. And after you do that, then we'll deal with B. So don't worry about B for now. Deal with it only if you finish early. Deal with this, we'll work this out, and then we'll worry about the frequency response. Make sure you use the convolution equation. You don't know what the shape of the signal x is, so trying to draw, flip, and shift doesn't really help you. But I haven't given you a signal shape x. Look at this summation that relates the output to the input. Think about how many terms on the right-hand side are non-zero, and write those out. This should not take you more than 30 seconds. Okay. Where's Meatball? Meatball here? Oh, he's not here, actually. He told me something. So who wants to take over Meatball's job today? Ali. And then there was light. You are? Zach. Okay. Okay. Speak a little louder, Zach, so everybody can hear you. Convolution sum. How many terms are non-zero? 2. K equals 0 and K equals 1. So you have h of 0, x of n, plus h of 1, x of n minus 1. Both of these h values are 1/2. So you're left with x of n plus x of n minus 1 divided by 2. And that's the relationship between the input and the output. So if you're plotting the 2-day moving average curve for the stock that you're interested in, the value of the average today is today's closing price plus yesterday's closing price divided by 2. Okay? Now let's look at the frequency response. Did you get a chance to work on that? I gave you plenty of time. Okay. So you want to carry that on, Zach? Go for it. Don't let your voice taper off. They're going to get bored. Make sure they all hear you. There are only 2 non-zero terms here as well. H of 0 times what? E to the 0, which is 1, plus H of 1 times e to the negative I omega. And what does that give you? E to the negative I omega. This is H of omega. Okay. I'll leave this here. Now there's one thing I'd like you to notice about frequency responses of discrete time LTI. Important observation. Of discrete time LTI systems. For discrete time LTI systems, where you have h of omega equals where h of omega is the sum of hk e to the minus I omega k. Notice when I change omega to omega plus 2 pi, well, actually, I'm not going to give you the answer. You figure it out. What happens if you replace omega with omega plus 2 pi? In other words, you take the curve, whatever the function is, h of omega, and you shift it by 2 pi. In this case, I've shifted it to the left, but it doesn't matter. The point is it's a 2 pi shift. Tell me what you get. So this is an aside box before we proceed with that example. Instead of omega, plug in omega plus 2 pi, and simplify as much as possible, and tell me what result you get. Zach, you want to pick somebody to answer the... Wrong answer. Wrong answer. Your name is Tim. Well, I don't know what you guys talk to each other about. The whole class has to hear you. This is not for me. Well, it is, but... H of k. Mm-hmm. Pop what up? Sounds like a gangster. Pop his head out. HK. E to negative I omega k. So far it looks just like before. Two pi k. K is an integer, so e to the negative I 2 pi k is what, people? 1. Thank you. And what's left? H of omega. So, for discrete time LTI systems, H of omega is equal to H of omega plus 2 pi. In other words, H is periodic with period 2 pi, which means when you want to plot it, all you have to do is plot it over an interval of length 2 pi. And you get to pick what that interval is. If you want to use 0 to 2 pi, more power to you. If you want to use minus pi to pi, more power to you. Depending on what the structure of H of omega is, one may be preferable to the other. Okay, so when plotting things like the magnitude of the frequency response, notice H of omega in general is a complex valued function. For some systems, for some impulse responses or time domain signals, it may turn out to be real. But in general, you get all these complex exponentials sitting in the definition right here. So in general, you get a complex valued function. So usually what we do is we plot the magnitude response. This is called a magnitude response. Or the phase, which is called the phase response. Pick an interval of length 2 pi that's convenient. I'm going to leave this here. I'm going to use a notation in this class whenever I want to talk about an interval of length anything. Open angle, closed angle with some number denotes a contiguous interval of length 2 pi. Okay? So That interval can be 0 to 2 pi. Where's my red chalk? Or minus pi to pi. So that's one example. Or, whoops. Usually these are the two that we pick. Okay? You can, of course, pick others, but in the many years I've been teaching this, I've never found any interval other than these two that will be useful. So now let's go back to our example. Back to our example. H of omega, Zach found to be 1 plus e to the minus I omega over 2. Now, before we plunge into doing any kind of mathematics, I want you to think about what kind of a filter this is. We have different types of filters. We have low-pass filters. Let me draw the unit circle. Remind ourselves of what low-high frequencies were. For discrete time signals and systems, what are low frequencies? Around 0 or multiples of, so low frequencies. And what are high frequencies? Around pi or odd multiples of pi. High frequencies. And others are considered intermediate frequencies. A low-pass filter, low-pass filter, or an LPF, favors low frequencies. Duh. A high-pass filter favors high frequencies. A band-pass filter favors mid-range frequencies. Anything that's not high-pass or low-pass will be band-pass. There are other kinds of filters. There are notch filters that get rid of everything except, or pass everything except a particular frequency. There are anti-notch filters that kill everything except one frequency. And they all have applications, and you'll get to do some of these things in the lab and also in some of the problem sets. And occasionally we'll have examples of those. But a low-pass frequency, a low-pass filter is a filter that favors low frequencies and kills high frequencies. So if you want to describe that in a layperson's term, what is it doing to a signal? Let's say you're looking at a stock signal, and you're applying this 2-day moving average. What does it do to the signal? Layman's term. Layman doesn't understand amplitude. Removes the extremes. Smooths the signal. Okay? So the original stock price data may be jaggedy, like these days. And the 2-day moving average smooths it a bit. 3-day moving average, you expect to smooth it more. 5-day moving average, more. Huh? Because it's taking the average of two adjacent values. Averaging is a smoothing operation. And the larger the number of days you average over, the less the effect of the next price fluctuation will be on the overall moving average. Because it's fighting against all the inertia of the previous days that are going to count in the moving average. And there are all kinds of variations of this. So in this case, today's stock price weighs as much in your moving average as yesterday's stock price. Each of them has coefficient 1/2. And some of you, again, those of you who dabble in the stock market have probably seen, if you go on Yahoo or Google Finance or what have you, I'm sure a whole bunch of them have this feature. You can do exponentially decaying moving average, where today's stock price counts more, yesterday's stock price counts less by an exponential factor, the day before counts even less by an exponential factor, and so on. So there are variations of this. But this is a simple 2-day moving average that we can analyze now. So let's do that. So I want to figure out what the magnitude of the frequency response is. And I expect it to have a peak around 0 and die out as I go toward pi and minus pi. So already I'm favoring the interval minus pi to pi in what I'm saying, but it doesn't have to be that way. We'll see. So here's what I do. I have two terms that have the same coefficient, but have different exponentials. This one is at 0, this one is at minus I omega. One of the tricks I use is try to make the exponentials have opposite polarity. So I can pluck out a sine or a cosine. How do I do that? What do I pull out? E to the negative I omega over 2. If I pluck that out, what do I get in the fraction? 10 seconds. No, 10 seconds. Do it. All right. Whom did you pick, Zach? Tim. Tim, you get to pick the next person. Who? Oh, man. Picking their friends. What do I have to multiply e to the minus I omega 2 over with to get a 1? Over 2. So when I multiply these two, I get 1. Then the second term. Omega over 2. That looks pretty nice, doesn't it? What is this? This is cosine of what? Omega over 2. So, I have now managed to convert h of omega into something that looks a heck of a lot friendlier. Cosine omega over 2 times e to the minus I omega over 2. Okay. Okay. Yeah. Ooh, didn't do it. Let me see what I can do this afternoon. I may be able to pull something off. Check your emails shortly before you come to office hours. So by about 5:30 or so. By 5:30 or so, check your emails and I should have an answer. Yeah, sorry, it completely escaped my radar. Huh? What was the question? Have I changed the location of the office hours because it's cramped? I've never had this problem. I don't know what's going on this semester. I'm becoming, huh? Well, it could mean one of several things. Either I'm becoming more popular. It can't mean that the problem sets are getting harder because I'm using pretty much the same problem sets. Well, let's not talk about the third possibility. Oh, man. All right. So we have a frequency response. It's a complex valued function. Notice I've got a real part and a complex exponential. So this is not a real valued function. It's not quite in polar form either. Because cosine theoretically can go negative. Right? Cosine can go negative. If I had it in the form alpha e to the I theta, and alpha was guaranteed to be non-negative, then I automatically have it in polar form. And I would say, okay, alpha must be the magnitude of this function. That's not the case with cosine. Cosine can go negative. So, strictly speaking, the magnitude of h is what? Absolute value of the? What happens to the complex exponential? It's 1. Right? Magnitude of a product is the product of the magnitudes. So you've got the magnitude of the cosine times the magnitude of this complex exponential, and we know that's 1. Well, why don't you plot this for me? Whatever gets you excited, man. So plot this. If you want, you can plot it from 0 to 2 pi. If you want, you can plot it from minus pi to pi. Just do it. Minus pi to pi is probably a little better. Remember, whatever shape you get has got to be consistent with the low-pass filter. And I'll say a little bit more about the smoothing operation and low-pass filtering, because apparently there's some confusion still. Yeah. So the magnitude is what determines how much each frequency is attenuated or amplified. Yeah, exactly. Okay, Yash. Your turn to pick somebody. Young lady. Where? You are? Yvonne. Go for it, Yvonne. What does this look like? It doesn't have the negative part. So when I'm at 0, what do I have? Actually, why don't you gesture with your hand? If I want to plot this from here to here, what do I do? You did it from 0 to pi? Sure. It's 1. Let's not go into that level of detail. Tell me where you get to by the time you get to pi. Cosine of, when omega is pi, what do you get? Cosine of? And what's that? 0. So you know it's 1 here, 0 here. If you were to plot just the cosine, what would it be like? 0, pi, 2 pi, minus pi, minus 2 pi. Forget about the absolute value. If you were to plot it from minus 2 pi to 2 pi, what would it be like? At 0, it's 1, you said. And where does it cross 0? Actually, maybe this is a little confusing. Let's do it this way. Let's do minus pi to pi, 0. Okay, so it's 1. And then what? Maybe this will help you. Cosine is this wave, right? I'll draw that for you. And you said this is at 0 frequency. And let's say this is my axis. This is at 0. Where is this? Pi over 2. And this is at minus pi over 2. So, this is cosine omega. If I were to plot cosine omega over 2, again without the absolute value, what would it be like relative to this curve? Am I compressing it along the omega axis or stretching it? Stretch. So the first 0 crossing, instead of it being at pi over 2, is going to be now at what? Pi. So this portion of the curve, which went from minus pi over 2 to pi over 2, gets stretched by a factor of 2. And so this whole curve now extends from minus pi to pi. So it turns out, over this length 2 pi interval, you don't even have to worry about the absolute value sign. The cosine ends up being non-negative anyway. So this is my h of omega magnitude. Is that a low-pass filter or a high-pass filter or what? Low-pass. It favors low frequencies. And as you go toward higher frequencies, remember, minus pi and pi end up in the same place on the unit circle. And so frequencies near pi and minus pi are considered high frequencies. And this filter, in fact, attenuates more and more as you go toward the highest frequencies. Yeah? Can h of omega, without the absolute value sign? With the absolute value sign, obviously not. Yeah, without the absolute value sign, in fact, it doesn't even have to be real, so forget about negative or positive. But for some filters where h of omega, see, it doesn't matter that h of omega goes negative. Let's say h of omega is real. For some filters, it's real. For example, a three-point moving average like this, 1/3, 1/3, 1/3, h of omega ends up being real. That's a nice exercise for you to do at home. Do this at home. Try this at home. That's the thing. So, but it doesn't matter that it goes negative in some frequencies. What matters is the magnitude, because that's what determines the amplification. So this, in fact, ended up being a low-pass filter. What is it doing to frequency pi? To what? The completely kills it. This filter completely kills frequency pi. Well, let's see. So, x of n, one of the things we learned last time is that, and also this time, when x of n is e to the I omega n, and it goes into an LTI filter, it comes out as h of omega e to the I omega n. Okay? There's mathematical terminology for this, which says that complex exponentials are eigenfunctions of LTI systems. And all it means is that when you send the complex exponential e to the I omega n, you get something that's a multiple of that complex exponential. Some of you who are a little more advanced with your linear algebra have seen eigenvectors, where there are certain vectors that when you multiply by a matrix, you get the same vector out multiplied by a scalar. This is just a functional analog of what you see in linear algebra. Some vectors have a special relationship with the matrix that they're multiplying, such that when you do that multiplication, you get the same vector out. You get another vector that's along the same direction as the original vector, where the magnitude and the direction is determined by this lambda, which is a constant. So these are eigenvectors. Here we say eigenfunctions. Oops. Eigenvector. Don't worry too much about the terminology. What's important is this. If my input signal doesn't contain a particular frequency, the output signal cannot contain that frequency. In other words, an LTI system cannot create a frequency out of nothing. It can kill a frequency that is present in the input signal and make sure that it doesn't come out at the other end. But if a particular frequency is not in the input signal, it sure as heck is not going to be created in the output signal. So, LTI systems cannot create new frequencies. Nonlinear systems can. A system that squares the input can create a new frequency. What happens when I send an e to the I omega n into a square? 2 omega n. So the frequency omega at the input has now been converted to 2 omega in the output. But LTI systems cannot create new frequencies. And you can use this to disprove LTI-ness of a system. Yeah? No, time-varying systems can also create new frequencies. You need both those properties. So here's the logical, but we won't dabble too much in that. So if a system is linear and time invariant, then read my lips. No new frequencies. You know, a few years ago, back in 2000, when I said this, nobody got it. That's when I realized how old I was. Nobody knew Bush Sr. Okay, so linear and time invariant implies no new frequencies. That means even a single frequency implies what? Not linear or not TI. Okay. Now that after that lesson in logic, let's get back to our filter. So we notice this system kills frequencies at pi. So I want you to tell me, without doing any math, well, maybe we're doing this much math, what the output of the system is of this filter when the input is minus 1 to the n. Why? E to the I pi n, right? Minus 1 to the n. Notice minus 1 to the n is what? It's the signal that keeps flip-flopping. Politicians are very high-frequency people. Okay? This is the input signal, x of n. In a previous lecture, I told you this is the highest frequency discrete time signal you can find. So you can represent that as e to the I pi n. And so what comes out at the output is what? Y. H of pi times I pi n. So what comes out is h of pi times minus 1 to the n. What is h of pi? 0. And so the 2-day moving average completely kills this signal, which you'd expect, right? Any two adjacent values you take the average, you get 0. That's exactly what it does. Huh? Whatever gets you excited. I'm here to entertain. Throughout the 15 weeks, my role is to entertain you. Only on maybe 5 or 6 occasions, our roles get reversed. And those are during exams. That's when you entertain me. Well, even then I entertain you. But at least I get something in return. Okay, now what happens to the constant signal? What happens if you send in the signal x of n equals, let's say, 1? What do you get? H of what? 0 times 1, which is e to the I 0 n. This is equal to e to the I 0 n. And h of 0 is what? 1. So you send the constant signal in. Obviously, you'll get the constant signal out because it's doing the 2-day moving average of this. You take any adjacent days, you average it, you get the same thing back. Right? Now, part of what you have to do after we go through an exercise like this. So this is a very simple discrete time filter. Can you think of a way to change this? Oh, actually, before I do that, what's the phase of this filter? Negative? This belongs to a special class of filters called linear phase filters. And they have nice properties that you'll study in probably EE123. And linear phase filters usually result from filters that are finite in duration and have some kind of a symmetry or anti-symmetry. In this case, you have a finite impulse response. It's got only two non-zero values, and there's symmetry across the values. So those kinds of filters usually produce linear phases. Now, can you fiddle around with this filter to change it into a high-pass filter? These are the kinds of questions that I want you to ask yourself to get into my mind and see what new problems I can throw your way. Usually I don't have to do a whole lot to existing problems to throw something new your way. I can perturb problems just a tad bit, and it'll throw enough of you out that we can have a nice curve in the exam score. But the way to fight that is to try to figure out, with some of these examples, what you can change to turn the problems around a bit. So here I had a 2-point moving average. 1/2, 1/2. Okay, with 0 everywhere else. By the way, I use the term finite impulse response Some books use finite duration impulse response. And they all call it FIR, filters. When you look at the impulse response and it's non-zero over only a finite range of values. So this is an FIR filter because its non-zero values extend over a finite interval. In other words, it's got a finite region of support for those of you who get excited with math terminology. Okay. And I know you're out there. Closet math geeks. Now, this was a low-pass filter. We tested it out on the constant signal, which is the lowest frequency signal, and the signal that flip-flopped from sample to sample. How would you design a high-pass filter without changing much here? Can you give me a 2-point high-pass filter? You don't have to prove it right now. Just conjecture what its impulse response would be like. Yeah?
So n at 0 would still be 1/2, and then n at 1 would be negative 1/2?
Negative 1/2. 1/2, 1/2. This is, call it G, 2-point moving differencer. Now that you've gone through the first filter, can you tell me what the output is in terms of the input? What's your name?
Jeremy?
Jeremy. Can you tell me what it is? In the other case, it was y of n equals
1/2.
x of n plus x of n minus 1 over 2. What is this one?
So 1/2 x of n minus 1/2.
X of n minus x of n minus 1 over 2. H of omega in the G of omega will be related to the other one. How? The other one was 1 plus e to the minus I omega over 2. 1 minus e to the minus I omega over 2. Mathematician's joke, remember? Convert it to something you've already done. Don't reinvent the wheel. Now, since you have a difference here, when I pull my half power of the exponential out of a hat trick, I get an e to the I omega over 2 minus e to the minus I omega over 2 over 2. What is that? It's related to a sign. So you have, but it's not quite a sign because I don't have an I in the denominator. So it's sine omega over 2 times I times e to the minus I omega over 2. Now, I don't like these i's floating around here. So I changed that. Well, how do I get rid of the I and absorb it into the exponential? Phase shift. So this is minus, let's make it I minus omega over 2 plus pi? Pi over 2. Now when you plot the magnitude response to this, notice how much faster we're going through this problem? It's sine omega over 2. And when you plot it, what do you get? From minus pi to pi. What is it at 0? Actually, this one, it may be easier to plot from 0 to 2 pi. But you can compare it with the other one better if we do it from minus pi to pi. But so let's do minus pi to pi. 0. And then what? And if you want to plot it all the way to 2 pi, it'll be like that. 2 pi. Okay? So when you look at this interval, notice it kills DC signals, constant signals. And that's what you'd expect. Because if you give this system a constant signal, adjacent values are the same. When you take their difference, you get 0. So it's killing the DC value. And when you apply this signal, it takes this value and subtracts the previous value. So it highlights the differences or variations between adjacent samples. So the faster the variations in a signal, the higher the frequency components that are present in that signal. The smoother the signal, the lower the frequency components. So if a signal is already smooth and you send it through a low-pass filter, it's not going to change much. If a signal is varying very fast like this one and you send it through a low-pass filter, it's going to get rid of this substantially or completely. We'll pick up next time.